In this video, we're looking at the definite integral of x over x squared plus pi on the interval -1 to 1, and we're going to approach the integral in 3 different ways. So I labeled these as a good way to do it, a better way to do it, and the best way to do it. Our good method is an explicit u-substitution. So what I have to recognize here is that I basically have the derivative of the denominator sitting in the numerator. This inspires me to let u equal the denominator here. So u is x squared plus pi, which means du is 2x dx. And I'll go ahead and transform the limits of integration while I'm working. So when x is equal to -1, I plug that into the definition of u, and I get a 1 plus pi because -1 times itself is +1. So I get u is 1 plus pi. And when x is +1, I plug that into the definition of u, and again, I get 1 plus pi. And this tells me immediately what's going to happen to this integral when I rewrite it. It becomes the integral from 1 plus pi to 1 plus pi. Well, the interval width is 0, so I know this integral is going to vanish, but just for completeness, let's finish the rest of the interior of this thing. So du is 2x dx. If I just pop a 2 into this integral, I have 2x dx, that's du, and then I put a 1/2 out in front to compensate. So I have a 1/2 and then a du divided by u. That would integrate to a natural log absolute value of u, but I don't even have to do it because when you're integrating over an interval that has 0 width, this integral is going to vanish. So we get 0, and that was a good way to do it. Let's look at a slightly better way to do it. And all I mean is that we're going to try to see the chain rule backwards instead of doing an explicit u-substitution. So it's exactly what I already started to do up here. You put a 1/2 in front, you build the derivative of the denominator inside your integrand, and you get a 1/2 integral from -1 to 1 of 2x over x squared plus pi dx. Now, anytime you have 1 over something multiplied by the derivative of that something, you can recognize this as coming from the natural log of the denominator. So I get a 1/2 natural log absolute value, and that's not really necessary because x squared plus pi is always positive. Natural log absolute value x squared plus pi evaluated from -1 to 1. Now, when you're using the chain rule backwards, it's always good to at least mentally check that it's working. So when I differentiate this natural log, I get 1 over its argument, which I see right there, multiplied by the derivative of the argument, which I see right there. So it's all working. Now, when I plug in the upper and lower limits, I can see those are just going to cancel out again. So I end up with a natural log of 1 plus pi when I sub in the upper limit, minus a natural log of, well, -1 squared is just 1, so 1 plus pi. When I sub in the lower limit, those two cancel each other out, and again, the integral vanishes. Now, what's the best way to do this integral, in my opinion? The best way is to see the symmetry of this function from the very beginning. So what I recognize here is that x is an odd function. That's in the numerator. X squared plus pi, that's an even function. And anytime you have a product or quotient of an odd function and an even function, you're going to get an odd function. And I'll post a link to the video where I first introduced these symmetry issues. Now, if you want to explicitly prove that this integrand is an odd function, all you have to do is evaluate it at -x. So suppose I call the integrand f of x. What I would do to test the symmetry of this function is evaluate it at -x. And that gives me a -x over -x squared, but that's just the same as x squared, because the minus signs cancel. And then I realize what I'm looking at here is the negative of the original function f of x. Now, anytime f of -x is equal to the negative of f of x, it's an odd function. So there's your proof if you want to be a little more rigorous. And now to remind you of the symmetry of odd functions, we'll bring in a picture of this thing. And odd functions have this 180-degree rotational symmetry about the origin, and that means they spend exactly as much time above the x-axis as they do below if I integrate on an interval symmetric about the origin, -1 to 1 in this case. So we can see immediately by symmetry that the integral vanishes. So I can say it's equal to 0 by symmetry. So whether you do the integral the good way, the better way, or the best way, all 3 approaches agree with an answer of 0. And I think a useful way to look at this is that as you get more experience studying math or applied math or physics, you want to move your way from left to right on this screen. So you start out with explicit u-substitutions. With practice, you start to skip a lot of those by seeing the chain rule backwards. And then as you get really good at applying mathematics, you're just always hunting down symmetries. You're looking for things that vanish wherever you can find them in order to simplify larger calculations. So hopefully this video has made you somewhat more likely to look for this type of symmetry in the future. I'll post a link on the lower left to a video where we bypass an integral of a sine function by using a periodicity argument, which is a different sort of symmetry argument. Thanks for watching.